What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 3, Section 2, Domain and Range. Let's do it. Question 1. Why does the domain differ for different functions? Domain really is all about what we're allowed to input for x. So normally for most functions, we want to think that we start with the assumption that you can input any value for x. Really, it's about the restrictions. What values are going to make us go into imaginary or non-existent territory. So there's basically two places that you want to look. Number one, if we take a square root of a negative value, that's going to take us out of real numbers into imaginary numbers. So that would be a domain restriction, right? If we have the square root of x, -3 is going to be out of bounds. Likewise, if we have a function like 1 over x, for example, another restriction we want to watch out for is we don't want to be dividing by 0, right? So again, 0 would be part of that domain restriction. So again, depending on the nature of the function, we're going to have different restrictions, aka different inputs for x that are viable, which means different domains. Explain why the domain of f of x of cube root of x is different from the domain of the square root of x. So the reason why these have different domains is, once again, we go back to that idea of what is allowed, meaning what is going to send us into imaginary territory and what isn't. Well, here's the nice thing about the cube root of x. There's nothing that's going to make this imaginary. You can take cube roots of negative. For example, the cube root of -8 is -2, right? -2 times -2 times -2 is indeed -8. We cannot say the same thing about even roots, aka a square root. For example, the square root of -4 is not going to exist. We're not going to get a real number, either positive or negative, that when you multiply it against itself is going to be negative. Because as we know, a negative times a negative is a positive, positive times a positive is a positive, so you're kind of stuck. Hence, this guy right here is going to have all real numbers in the domain, whereas this one here, it's going to be everything, including 0 all the way up through infinity. Boom, done. So when we talk about how to graph a piecewise function, let's first take an example of what a piecewise function is. I'm going to take a pretty nice straightforward example. And what is a piecewise function? It's basically two or more functions that are merged together. Now, you might first wonder, what's here on the left-hand side? You'll usually have some sort of an inequality. That's to define the domain of the particular function we're talking about. So for example, when I say x is less than 0, I'm saying whatever the function is up here is only going to take up to -infinity up through 0. So for example, if I had x squared as my function, we'll just put a little comma there. It's only x squared where the values of x, where the domain values are less than 0. And then if I had a function here of 2x, when x is greater than or equal to 0, this is for all the positive values, we'd be plugging them in to this function of 2x. And then now if we're talking about graphing it, we can see that on the left-hand side, right, we're going to have this function. So everything less than 0. So we know x squared is a parabola. And by the way, at 0, this thing does not exist because it says less than 0. So we know when you plug in 0 here, 0 squared is 0. And then think about it. Then if we plug in -1, -1 squared is 1. So we'd have another point here. -2 squared is 4. So let's say we come up, we got 1, 2, 3, 4. Now we get a second point here. And this is what we would expect, a parabola going up to the left. Again, it would normally continue on, but the domain is restricted, only values less than 0. So what about for 0 values greater than or equal to 0? Well, now we're going to use this function 2x. So now we plug in values on the right-hand side into this function. Well, we know at 0, it's still going to be 0. We can fill that in. Then at a value of 1, it's going to be 2 times 1, which is 2. At a value of 2, it's going to be 2 times 2, which is 4. And we know that y equals 2x is a linear function. So that's validated here in these couple points we plotted. And then out to the right, let's get this lined up a little better. Out to the right, we have this type of situation, a line. Let's match that thickness. And there you go. So that's how we're going to graph a piecewise. You look at the domain restrictions or the sort of domain of each function, plot that function within the domain, boom, done. So for this function, we're trying to find domain. Again, when we're talking about domain, we're really looking at what are the domain restrictions? What can we not plug in for x? Meaning what values of x are going to give us either a square root of a negative or a dividing by zero situation. Well, this is a quadratic. I can plug in anything I want for x. It's just going to be that value squared. So there's no restrictions, no limitations, hence it's all real numbers. Now, the way we say that in interval notation is anything from negative infinity up through positive infinity. And since infinity is not really a number, it's more of a concept, we're not including, right? You might wonder, hey, why don't we have brackets? So just think, when we're talking about infinity, we're not inclusive. We're using the curved parentheses, boom, done. For this function, we have a square root. So once again, we know that when we're taking a square root, the value inside the radical cannot be negative. Otherwise, we're going to go into imaginary number territory. So the way we represent that is the value inside the radical must be greater than or equal to 0. Again, it can be 0. That's fine because square root of 0 is 0. Now we're going to isolate. We're going to subtract 6 from both sides. Boom. We got negative 2x is greater than or equal to negative 6. Then we're going to divide by negative 2. And don't forget, when we divide by a negative, we flip the inequality, which leaves us with x is less than or equal to 3, positive 3, right? Negative 6 divided by negative 2 is positive 3. So we can go as high as 3, but then anything below that is good to go. So how do we represent that? Well, anything below means we're going all the way to negative infinity up to and including 3. So we give that square bracket, boom, done. So once again, we have a square root situation. So we want to be conscientious of not ever having a value of x that we plug in that's going to make us take the square root of a negative. But in this case, we have something interesting going on. Underneath here, we've got an x squared. So the thing you might remember is there's no way I'm getting a negative value when I'm plugging something into an x squared, right? Negative 2 squared is positive 4. Negative 10 squared is positive 100. 0 squared is 0. That's fine. And then going up the other way, obviously all positive values squared are also positive. So this is going to have no domain restrictions, meaning we got all real numbers, aka negative infinity to infinity. Boom, done. For number 13, we got a cube root situation. And as we mentioned in a previous problem, cube roots are good. There's not going to be an issue of taking a square root of a negative. Again, it's also about even roots. We don't want a fourth root of a negative, a sixth root of a negative. But this is an odd index, an odd root. I can take a cube root of a negative all day long. Once again, all real numbers, negative infinity to infinity, boom, done. For number 15, we have a rational function. So now we're not so concerned about square roots of negatives. We're concerned about dividing by 0. So when are we going to divide by 0? When this denominator, 4x plus 2, equals 0. So literally, we take this equation, we solve for x. So check it out. I'm going to subtract both sides by 2, and we've got 4x equals negative 2. Then we're going to divide by 4 like so. Boom. Negative 2 over 4 simplifies to negative 1/2. So again, what did we solve for? We solve for what x cannot be, right? So x is not allowed to be negative 1/2. So as we translate it to interval notation, it can be anything but that one number. So check it out. We're allowed to go as low as negative infinity up to negative 1/2, but then we exclude it. And then we join this with another set because we can go from negative 1/2, again, not including it, but all the way up to positive infinity. Let me make a little room here. So now we have positive infinity, and there is your full interval for the domain. Boom, done. Once again, here we have a rational function, and we want to make sure that we're not dividing by 0. So we need to figure out what values of x are going to make this denominator equals 0. Well, of course, it's a quadratic, so let's see if we can factor this guy, right? So what two numbers multiply to negative 22 and add to 9? Well, that would be negative 2, and positive 11, right? They multiply to negative 22. 11 plus negative 2 adds to 9. So what two values are going to get us to 0 here? It's going to be positive 2, negative 11. Now remember, what were we solving for? We're solving for domain restrictions. These are values of x that we cannot have. So now when we get our domain, it's everything from negative infinity up to negative 11, right? We're doing the smaller one first, not including negative 11, then going up from negative 11 all the way up to 2, again, not including 2, and then from 2 all the way to infinity, and that gives the full domain. For this function, once again, we're looking for values that will make the denominator go to 0. That's going to be our domain restrictions. So I'm going to take that denominator and set it equal to 0. So we got this nice situation. Let's factor because it's a quadratic set equal to 0. And to factor, we say what numbers multiply to negative 15 and add to negative 2. That would be negative 5 and positive 3. That gives me a product of negative 15, a sum of negative 2. And what are the values that now are solving this equation? It would be positive 5 and negative 3. But once again, remember, these are our domain restrictions. These are what x cannot equal. So now let's define the domain. So we got everything from negative infinity up to negative 3, but excluding it, of course, negative 3 up through 5, and then again excluding 5, that's why we have the curved parentheses, and then starting again at 5, and then going all the way through infinity, boom, done. Here we got something interesting. We have a radical and a rational equation for the function. So we're talking about domain here. What we want to recognize is the denominator both has to be positive underneath the radical, and it cannot equal 0. So how do I represent that? Well, I'm just going to say 5 minus x has to be greater than 0. Normally, if it was just a radical, I'd say it can include 0. But here, because it's also in the denominator, we have to exclude 0. Now I got this nice inequality. Let's subtract 5 from both sides to isolate x. Negative x is greater than negative 5. Multiply both sides by negative 1, so we get positive x, and then we flip the inequality anytime we divide or multiply both sides of an inequality by a negative. So we get x is less than 5. These are the viable values. And then to put it in interval notation, it's everything below 5 up to and not including 5, hence the curved parentheses, boom, done. So for this function, it's kind of interesting because we have radicals in the top and the bottom. So we kind of got to think about both of them, right? And what we're going to do is let's look at the domain for each, and then we can kind of figure it out from there. So the bottom one, we know that x minus 4, it can't equal 0 because it's in the denominator, and it has to be positive, right, this value here. So we're going to say x minus 4 is greater than 0. For the top restriction, right, we have a different limitation. It can be 0, but it has to be still positive, right? So x minus 6 has to be greater than or equal to 0. So let's solve both of these. This one by adding 4, we get x is greater than 4. This one by adding 6, x is greater than or equal to 6. So now we got two kind of different values of domain. So the question is, which one do we use here? Well, we have to take the more limited one, because if I say, fine, x is greater than 4, well, wait a minute. That means 5 is viable. But if I plug 5 in on the top, I get the square root of negative 1. That, again, takes us out of real numbers. So this one is more limited, right? If we look at it on a number line, it's like, hey, this one is saying everything greater than 4, and this one is saying everything greater than or equal to 6. Well, we kind of have to look at the overlap of both of these guys, right? Because that's the real domain. It has to be viable for both the top and the bottom for both those radicals. So this is our real winner. And then if we put it in interval notation, we're starting at 6, but we're including it, taking it all the way up through infinity. Boom, done. So for this function, once again, we're concerned about the denominator equaling 0. So what I'm going to do is I'm going to say x squared minus 81. We want to see when this equals 0. Now, you might recognize this as a difference of squares, where we can factor it like so. The square root of x goes here and here. Sorry, the square root of x squared, I should say, which is x. And then the square root of 81 is 9, which goes here and here. This is how we factor a difference of squares. And then we got plus and minus. You sort of alternate plus, minus, plus, same thing. And what two values are going to satisfy this equation? Well, it's going to be negative 9 and positive 9. And once again, these are values that are restricted from our domain. So if we want to represent this in interval notation, it's going from negative infinity all the way up to negative 9, not including it. Then we start again at negative 9, going up to positive 9, again, not including that or excluding it. And then we're going from 9 carrying up to infinity. Boom, done. For this one, we want to figure out the domain and the range. So as we've seen, domain are all the viable x values, or the x values that exist for this function. So it's pretty visually apparent because the x values, they start at 2, but again, it's an open circle, so we don't include that. And it goes up to and including 8, so we got that nice square bracket. Well, what about the range? What's that? Range is all of the y values contained by this function. So we're going to go from bottom up. We see that the lowest value that's included is a 6. So again, it's filled in. So we're going to do a square bracket for 6. going all the way up to 8 on the y-axis, right? We're now looking at the y values. So 6 up to 8, but not including it because it's an open circle. Boom, done. For the domain here, we've got values starting back at -4 inclusive, right? So if we're talking about domain, we're starting at -4 with the square bracket, going all the way up to +4 with a square bracket. When we're talking about the range, now we're looking vertically. The lowest it goes is 0 on the y-axis, and the highest it goes is 2 on the y-axis. So I'd say the range includes 0 up through 2 inclusive. Boom, done. For this graph, our domain starts all the way back here at -5 and includes values up to 3. So we got -5 included up to 3. But then we got an open circle there, so it's a curvy parenthesis. And for the range, we're looking vertically. The lowest value it looks like is 0, and it looks like it includes 0, going up to +2. Now here we have an open circle. Here we have a closed circle. But since there is a closed circle at one point, that means 2 is indeed part of the range. So we have a nice bracket. Boom, done. Now this one is interesting because we have an arrow indicating it goes continuously to the left, aka the domain is going to go all the way from -infinity, right, up to 1. And that's a hard stop at 1, including it. So we get a nice square bracket. For the range, likewise, we're starting at a bottom of 0, which we're including, and it appears as though it's continuing indefinitely up and to the left. So we'll say it goes from 0 to infinity, assuming it doesn't ever stop. It keeps going and going. And there's our winner. And don't forget, we always want a curved bracket for the curved parenthesis, I should say, for the infinity and -infinity. Boom, done. So for this one, we start at a value of -6 for the domain. So we're starting at -6, and then it kind of continues out to right here, which I'm not sure exactly what that value is from looking at it on the graph, but they give us the coordinate, and it looks like it goes up to -1/6. And it's including it, right, because it's a point there. So we'll say square bracket. And then we say union, and then it picks up again at +1/6. We're going to run out of room. I got to write tight here. +1/6, and then all the way up to 6. So you notice we're looking at those nice x values for the domain as per usual. Now let's talk about the range. The range, we're starting at a low point of -6 inclusive, going up to -1/6, right? Again, we're looking at the y values. Union, and then we're picking up again at 1/6 for the y value, going up to +6 inclusive. Boom, done. For this one, our domain begins at -3 on the x-axis. It's a solid point, so we're including that -3. And then it looks like it goes on infinitely to the right. So we'll say it goes to infinity. Again, a parenthesis, as always, for infinity. We're talking about the range. The bottom vertically looks like it's at 0 for a y value, inclusive, of course, going up to infinity, right? There's no upper bound. Infinity, boom, done. So when we're talking about sketching a piecewise function, I want to first recognize that this part lives where x is less than 1, where the domain is less than 1. So we can kind of have like a rough dividing line right there if we want to imagine that. But then what I always like to do is I always start at that boundary and I just do a little plug and chug. So I see at 1, when I plug it in, 2 times 1 minus 1 is 1. So I know I start with a coordinate of x equals 1, y equals 1. But because it says less than, not less than or equal to, that value is not actually included, but it gives us a starting point of an open circle that represents that the function doesn't actually exist there, but it kind of starts there, right? And then now to the left, again, this is for values less than 1. What is this? This is 2x minus 1. It's a line. But even if you don't know that, you can do a couple more plugs and chugs and get there anyway. So for example, the next value over is 0. Plug in 0 here, you get -1. So we got a nice point here. Let's get one more just for fun. Plug in -1, you get -2, because 2 times -1 is -2, minus 1 is -3. Check that out. And now you can kind of feel confident that this is a nice line. And that makes sense because it is a linear equation, right? With a slope of 2 and a y-intercept of -1. Now we got this part, and this is also going to be a line, right? 1 plus x, slope of 1, y-intercept of 1. But this is for values that are greater than or equal to 1, meaning including that value. So let's do our plug and chug. Plug in 1, 1 plus 1 is 2. So we got a nice coordinate at 1, 2. So we'll do a nice circle there. And then we'll do a little plug and chug beyond that. Plug in 2, I get 3. Plug in 3. I get 3 plus 1 is 4, as we expected. That's a nice slope of 1, so check it out. We're going to draw it out like this as best we can. I think that looks pretty good. And there's our piecewise function. Now it says, hey, give the domain of this function. So you could kind of give the domain from this. I mean, that is what domain means, right? It's where the x's live. But since there's no break, now you can look at it from the graph itself. There's no break in x's. There's nothing that doesn't exist. All the negative values and up to 1 exist, and then starting off at 1 again, we have new function values. So since that's the case, my domain is everything, negative infinity to positive infinity, boom, done. Once again, we're going to start this piecewise at these boundaries, at these limitations for x. So this one exists when x is everything less than 0. Well, what is that as a function? That's f of x equals 3. That is a horizontal line at 3. So that's nice, right? We can just simply graph this going to the left because it's for all values that are less than 0, right? Anything I plug in here, -1, 3, -2, 3, -4, 3, etc. But it does not actually exist at 0. It says less than 0. So don't forget we put a nice open circle here. And then when it's greater than or equal to 0, we got the square root function. So if you remember what the square root function looks like, it's approximately like this, but we can be a little bit more precise. So again, I'm going to start with a nice little plug and chug. At 0, it's 0, and that includes 0. So we got a nice point at the origin. And then I'm going to choose values that are easy to plug in. For example, square root of 1 is 1. I'm going to plug in 4. Square root of 4 is 2. So we got 4, 2. Plug in 9, square root of 9 is 3, so we got 9, 3, and that gives us what we predicted, a nice little Superman function, and there it is. And for the domain, once again, I don't see any breaks, right? There's a value for, that we can plug in any value for x and we'll have a corresponding function value. So once again, my domain is all real numbers, negative infinity to infinity, boom, done. Once again, we're going to start at that 0 value where x is less than 0. So I'm going to start by plugging that in. You plug in 0, 0 squared is 0, but it's not including 0, so we have an open circle. Now let's try a couple other values. -1 gives us 1, -2 in here gives us 4, and that's what we would expect, right? -3 gives us 9. A nice parabola to the left side. Let's see if I can get that look good. Yeah. All right, there we go. Now to the right, when x is greater than or equal to 0, it's x plus 2, which is again a line. Slope of 1, y-intercept of 2. But you don't need to know that. We can do plug and chug. Plug in 0, 0 plus 2 gives us a nice value of 2. Then we plug in 1, 1 plus 2 is 3. Plug in 2, 2 plus 2 is 4. That validates what we thought, right? It is indeed a line with a slope of 1 and a y-intercept of 2. And now we got a nice graph there to represent that. Once again, what's the domain? There's no values of x missing. We can plug in anything less than 0, anything greater than or equal to 0. There's no gaps. So my domain, once again, is all real numbers, negative infinity to infinity, boom, done. So up top here, we got an absolute value function, which you might recall is a V shape. So it's saying for every value less than 2. Again, even if we don't recall what the function looks like, we can do our nice plug and chug. So we start at 2, right? You plug 2 in, absolute value of 2 is 2. But we're not including 2, so that's an open circle. Then we can try 1. Plug in 1, absolute value of 1 is 1, absolute value of 0 is 0. Then we get to the fun part. Absolute value of -1 is 1. This is our V. This is what we are anticipating. Absolute value of -2 is 2, and so on. And now we've got our function, right? We're going all the way up to the left. That's like a nice slope of -1. And then, hold on, let me get this one up here. And then we got it connecting up to there, and boom. So there's our function to the left. Now it's saying it's 1 when x is greater than or equal to 1. Again, that's y equals 1. That's a horizontal line at 1, but we're starting at 2. So you plug in 2 here. Of course, it's 1. And we got a nice solid point. And then we're going to the right like so. Here, I'll just do a little arrow so that it continues. And there's our nice graph. Now, what's the domain? Once again, there's no break in the domain. It ends at 2 here, then it picks right back up, including 2 there. So my domain is all real numbers, negative infinity to infinity, boom, done. Here it's asking us to evaluate for these values of x, right? -3, -2, -1, and 0. So this is how we're going to do it. It's just a plug and chug situation. So first they want to know what's the function value when x equals -3. Well, when x equals -3, first you have to say what bucket does it go into? Well, these are for values greater than -3. So it doesn't go into this bucket here. It goes into this bucket, and here it says the function value is always 1, which means f of -3 therefore is 1. What about when f is -2? Well, that's greater than -3. Now we're going into this bucket, and in this bucket it says the function value is always 0. Likewise, for -1 and f of 0, those x values are also going into the bottom bucket, which means those values are also going to be 0. So these are your answers. Done. So for these ones, we're meant to evaluate f of -1, 0, 2, and 4. And it's again another plug and chug situation. So when f is -1, what bucket does it go into? This one or this one? Well, this one is saying for all values x is less than 0. So we're going to plug it in here. So let's do it in this guy. So 7 times -1 plus 3, that's -7 plus 3 is -4. Boom, done. What about f of 0? That's again greater than or equal to 0. So now we're talking about the bottom bucket. So plug and chug. 0 times 7 is 0 plus 6 is 6. What about f of 2 and f of 4? These are both going to be greater than or equal to 0. So plug in 2 here. 2 times 7 is 14, plus 6 is 20. And over here, 4 times 7, right? Plugging it in just for x. That's the function notation. 4 times 7 is 28, plus 6 is 34. Boom, done. So for this one, we're going to plug in -1. And the question is, what bucket does it go into? Well, that's less than 0. So we're going to the top bucket. 5 times -1 is -5. What about 0? This says x is greater than or equal to 0. So now we're in this bucket. So when we plug in 0, well, the function value is always 3. So there we go. Boom, done. Likewise, 2 is again between 0 and 3. The function value is once again 3. And then for 4, greater than 3, we plug 4 in to the final bucket. What's 4 squared? 16. Boom, done. For this one, we're simply meant to write the domain. And the beauty of a piecewise is that's the domain right there. That tells you where the x values exist. So the domain looks like everything less than -1. We're talking about -infinity up to 1, but not including 1, because even this doesn't include 1. So then we pick up at 1, not including it, with the parentheses all the way up through infinity. Boom, done. So for this one, we're going to graph 1 over x squared on these two different viewing windows. These are domain values, by the way. And so to do that and find the range, I'm going to show you how to do this on Desmos. So here's the function, and here's how you kind of limit the domain in Desmos. We kind of have this inequality in the squiggly brackets going from -0.5 to -0.1. And it looks like to find the range, it looks like the lowest it goes is 4, and the highest it goes is 100. So for this right here, my range is 4 to 100. Now, as we do the second part of the question, I change the domain from 0.1 to 0.5, and you can see that the range, interestingly enough, also is from 4 to 100, which is our top value. So for each of these, we have identical ranges, 4 to 100, boom, done. So for this function, it says the range is from -5 to 8. And then it says, what is the range of the absolute value of f of x? So what are we really talking about? If we're talking about a function, let's just give an example here, right? Here's -5, let's say, and here's +8. So let's just say right now, the function kind of goes like this, and then it goes up here. Again, I'm just making it up arbitrarily. So there's our function. And there's our range. We see we go as low as -5 up to 8. But when we apply an absolute value, remember, everything that's positive just kind of stays as is. But everything that's negative, right, we're taking the positive value. I call it the positive purifier. So it's almost like here, it's a value, let's say, of -1, then it would switch to +1. Here it's a value of -5, it would switch to +5. So you kind of get this interesting mirror image almost, right? And this would be the absolute value function. So what's the range in this case? Well, now the lowest it goes is 0. That makes sense because we can't get lower than 0 for absolute value. So my new range is from 0, still going up to 8, boom, done. So here I want to create a function where the domain is x is greater than 2, meaning I'm not allowed to throw in a value that is less than 2, essentially, right? Well, first I'm going to start with a nice square root function, right? Because if I say x minus 2 like that as a square root, remember, we can't take a square root of a negative. So this at least limits me to 2 or above, right? So that's greater than or equal to 2, but they didn't ask that. They said greater than 2. So we even want to exclude 2. Well, I can do that nicely by then throwing this in the denominator, because now we have to deal with the restrictions of a radical as well as the restrictions of not being able to divide by 0. So in this case, x would have to be greater than 2. Boom, done. Here we have a function for cost, and we're asked the following. What is the fixed cost, right? So the fixed cost, this is a linear equation. Fixed cost is usually my starting cost when x is 0, right? So in that case, that would be like the y-intercept, which would be 500. And then it said, what is the cost of making 25 items? Well, x is the number of items. This is straight plug and chug. So I'd plug in 25 for x and then see what I get. 10 times 25 is 250 plus 500 gives me a value of 750. Of course, this is in dollars, I assume, so we could even put a little $750 value if we wanted to. Last but not least, suppose the maximum cost allowed is 1,500. What are the domain and range of the cost function? So first, we're going to make a reasonable assumption, and that reasonable assumption is I can't make negative x items, right? So I know that my domain has to start at 0. Likewise, my range is going to have to start at that y-intercept. Since x can't go below 0, right? If I plug in 0 as the lowest value, this 500, this starting point, is going to be my bottom value for the range. Then it's telling us the maximum cost is 500. That is the y value. That is the range value. So I already know my max value for range is 1,500. And we're going to include that, right? But now the question is, what is x when we get a max cost of 1,500? So I'm going to do a little plug and chug. 1,500 equals 10x plus 500. And I want to know what this value of x is. So we're going to isolate. So I'm going to subtract 500 from both sides. Boom. We get 10x equals 1,000. Then we're going to divide both sides by 10. We get x equals 100. So that's the max amount of items I can make. That's my max domain value, max x value. So we go 0 to 100, inclusive, boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.